In Part 4 of our Test 1 review, we're going to look at problems 17 through 21 from Chapter 2. In problem 17, we're asked to determine whether or not f of x equals x plus 2 the quantity squared is a one-to-one function, and to give evidence to support our answer. There are two ways to approach this problem. You can do the problem graphically, or you can do the problem algebraically. Graphically, we need to actually draw a picture of our function and then apply the horizontal line test. We can see that x plus 2 the quantity squared is a parabola which has been shifted to the left 2 units. So if we draw a picture of this in our coordinate plane, we need to move to the left 2 units, so our vertex will be located at at negative 2, 0. Started to write that backwards. There we go. And of course this parabola opens upward. So the graph will look something like this. And then we apply our horizontal line test. So if we draw a horizontal line in the coordinate plane, we can see that that horizontal line is going to cut across the parabola in 2 points in very many places. So now we can write our conclusion. We can say that f of x is not one-to-one because it fails the horizontal line test. The other way to approach this problem is algebraically. In that case, we need to show that 2 different values of x can give us back the same value of y. So let's take a look at f of a. F of a would be a plus 2 the quantity squared. And let's look at f of b. F of b would be b plus 2 the quantity squared. Now we're going to make the claim that f of a is equivalent to f of b. That gives us a plus 2 squared equals b plus 2 squared. Now let's solve for a. So we need to take the square root. So that means that a plus 2 is equal to plus or minus b plus 2. So we now have 2 different equations to solve. A plus 2 equals b plus 2, and a plus 2 equals minus b minus 2. Solving the equation on the left for a gives us a equals b. But solving the equation on the right for a gives us a is equal to minus b subtract 4. So we see that there are 2 different values that give us back the same y value, a and minus b minus 4. So we can again conclude that f of x is not one-to-one. In problem 18, we are asked to find the inverse of the function f of x equals 4x subtract 3. And we are told that we may assume the function is one-to-one. So to find the inverse of this function, we need to reverse the x and the y coordinates for every single point. So that's x equals 4y subtract 3. Now we need to solve for y. So we can say that x plus 3 is equal to 4y, and that leads us to x plus 3 divided by 4 is equal to y. And since we were given function notation to start with, we should write our final answer in function notation. So f inverse of x is equal to x plus 3 divided by 4. In problem 19, we are told to use composition of functions to determine whether the given pair of functions are inverses of each other. That means that there are two stages to this problem. First, we need to look at f of g of x. So f of g of x will be 2 times the cube root of x minus 1 over 2, the quantity cubed, plus 1. And now we simplify. We know that cubing a cube root will leave us with the argument. So we now have 2 times the quantity x minus 1 divided by 2 plus 1. Now the 2's will cancel each other out, since one of the 2's is in the numerator and the other 2 is in the denominator of the fraction. This leaves us with x subtract 1 plus 1, and that leaves us, of course, with x. So far so good. But in order for these functions to be inverses of each other, we also need to check g of f of x. So going back, g of f of x is equal to the cube root of the quantity 2x cubed plus 1 subtract 1 divided by 2. So now we can see that underneath the radical, plus 1 subtract 1 cancels out and leaves us with nothing. And now we have the cube root of 2x cubed divided by 2. But 2 divided by 2 is really just 1. So we now have the cube root of x cubed. And the cube root of x cubed is equal to x. So now we can conclude that since f of g of x equals x and g of f of x equals x, f and g are inverses of each other. Problem number 20 is an application problem. It says a plumber purchasing materials for a renovation observed that the cost of copper tubing varies jointly as the length and the diameter of the tubing. If 20 feet of 1/2 inch diameter tubing costs $36.60, then what is the cost of 100 feet of 3/4 inch diameter tubing? Write your answer in a complete sentence using appropriate units. So we need to start out by taking a look at what kind of problem this actually is. So notice that it says that a plumber purchasing materials for the renovation observed that the cost of copper tubing varies jointly as the length and the diameter of the tubing. So that means that I'm dealing with a joint variation problem. So I need to define my unknowns and use that sentence to write down a formula. So I have the cost of the copper tubing. Let's call that C. I also have the length of the tubing. Let's call that L. And finally, I have the diameter of the tubing, which I'm going to call D. So now I simply take these values and plug them into the sentence. The cost of the copper tubing varies jointly as the length and the diameter of the tubing. So that's cost equals, varies jointly means I'm multiplying my length and my diameter by the constant of variation, K. So I get C equals K times L times D for my basic formula. In order to solve the problem, I need to be able to find K. Well, in that case, that means that I need a value of L, D, and C that go together. That's the next sentence. It says if 20 feet of 1/2 inch diameter tubing costs $36.60. So notice that I'm given a length, 20 feet, a diameter, 1/2 inch, and a cost, $36.60. So I'm going to plug those together into my basic formula. So that gives me 36.60 equals K. My length is 20 feet, so times 20. And my diameter is 1/2 of an inch. So 1/2. And now I simplify. So 36.6 is equal to K times 10. Divide both sides by 10 and I get 3.66 is equal to K. So I now know the constant of variation, and I can write down a formula specific to this scenario. C equals 3.66 times L times D. Now I'm ready to solve the problem. So I need to look at the last part, and it says, what is the cost of 100 feet of 3/4 inch diameter tubing? So, what is the cost means that C is my unknown. So I just copy down C. I already know K is 3.66. I've got 100 feet, that's the length, of 3/4 inch diameter tubing. So I'll plug 3/4 in for D. Now all I have to do is take my calculator and multiply 3.66 times 100 times 3/4 to get the value for C. When I do this computation, I get back that C is equal to 274.5. So now I simply need to take this and write my sentence and include my correct units. So now I can say that the cost of 100 feet of 3/4 inch tubing is $274.50. And I've completed the problem. Now we've made it to the final problem of the test, another application problem. It says that a cylindrical pipe with an outer radius R must fit snugly through a square hole in a wall. Write the area of the square as a function of the radius of the pipe. Be sure to use function notation. So what I really want, in order for this cylindrical pipe to fit snugly into this square hole, is for the edges of the circle to just brush up right against the edges of the hole in the wall. So what I can see looking at this is that if X is the length of the sides of my square, then that X is going to be equal to the diameter of my circle. But a diameter is 2 radiuses. So now I know that the length of the square is 2 times the radius of the circle. Now I know that the area of a square is the square of the length of the side. So A of X is equal to X squared. But I want to write this area as a function of the radius. So I'm going to replace my X's with an equivalent amount of R's. So X is 2R. So A of R equals 2R, the quantity squared. So finishing up my formula and simplifying, I get A of R equals 4R squared. And this would be my final formula for writing the area of the square as a function of the radius of the pipe.